This video is going to focus on enthalpy changes and how they take place along with chemical reactions. Remember from what we talked about previously that enthalpy is basically just going to be what your value of Q is, the amount of heat being released or being absorbed, especially if you are under a constant pressure situation. We represent enthalpy as a delta H. We look at the net difference from where we started at to where we finished at. When we see that degree sign, it's referring to standard enthalpy, and that means that we're under set conditions, kind of like we were with ideal gases. But we have a little bit different value for temperature. We tend to look at it at room temperature, 25 degrees Celsius, and at regular pressure of 1 atmosphere. And then the standard states are just representing that stable form. I gave you a chart of delta H values that we're going to use in the next video that have standard enthalpy of formation values for majority of the elements as well as key compounds. For pure substances such as elements or compounds, they are found in either the solid, liquid, or gas state, and if they are in solution, they are found at a concentration of 1 molar. When we are given enthalpy values for a reaction, the units usually are in some sort of joules, kilojoules or joules per mole, and the mole is representing the reaction as a whole, not a specific reactant or product. Typically, the reaction will be balanced with coefficients other than 1, and so the amounts will be represented for each substance in that equation in connection with those coefficients. In proportion would be the better word. So we'll see that in the first couple of examples I do with you. So if you do not see the word mole at the end, you would assume that the amount given to you in kilojoules is per however much of that reactant or product is made from the balanced equation. We can use the standard enthalpy values to determine how much energy is being transferred to the surroundings or from the surroundings to the actual reaction if it's endothermic. But we do have to account for the fact that heat released or absorbed is a extensive property, and so it is dependent on how much reactant or product is actually consumed. So the amount that we see, again, is per mole. If you don't have a mole, then you don't have that much energy being released or absorbed. If you have more than a mole, then you have more than that amount of energy being released or absorbed. So 1 mole of methanol here is being burned at constant pressure. When this takes place, 750 joules of energy is released, so this is exothermic in the form of heat. We want to calculate the delta H value for a process in which we burn only 24 grams of methanol. So we know that 750 joules of energy is released per mole of methanol burned. We need to figure out how the 24 grams compares to a mole of methanol. And the only way I know to do that is to convert grams to moles. So we're going to use the molar mass of methanol to get us from grams to moles. And that tells us that we're just under a mole. We're at 0.749 moles of methanol. The proportion I have tells me that there's 750 joules of energy released per mole. So I can figure out what percentage of that is being released for my 0.749 moles by either setting up a ratio or by using mole conversions. And that's the one I'm going to show you right now. But if you'd like me to show you the ratio one, just ask in class and I'll show you that. So we know that that's how much methanol that we burned, and we know that there's 750 joules of methanol or energy released per mole of methanol burned. So when I cancel out the moles and I multiply across, I see that roughly 562 joules of energy is released per 0.749 moles of methanol that has been burned. Going back to the equation and looking at the proportions, I told you in this statement that 1 mole of methanol was burned, and that's how much energy was released. So if you were going to balance the equation between methanol undergoing combustion, it would look like this. And if you notice at the end of the equation, the delta H value is roughly twice that, and that's because in order to have a balanced equation, you need 2 moles of methanol along with 3 moles of oxygen, 2 moles of CO2, and 4 moles of H2O. So because you would start with 2 moles of methanol in the balanced equation, the amount of heat released per 2 moles of methanol would be double. And so if we go back and divide the 1500 by 2, you go back to the 750 that was provided in the statement for this question. So if you were given a reaction and asked to use that to figure out how much heat was released or absorbed for a reactant or product, you would take the delta H value that's given to you and divide it by the stoichiometric ratio for that reactant or product. And if that's not clear, just ask and I will try to explain it a little bit better. So what we're going to look at now are calorimetry problems. We've seen this actually a little bit already with physical changes. We're going to look at it more from a chemical change perspective. And you're going to get to do this in lab. It'll be our next lab where we combine different reactants together and measure temperature changes in terms of the heat being released or absorbed by the solution so that we can figure out how much heat was released or absorbed by our reaction. Remember, we have to look at it from both the system and surroundings perspective. We can always measure temperatures of our surroundings and use that to find the energy associated with a reaction. Constant pressure, again, is typically done for both chemical reactions and physical changes. Constant volume takes place when we tend to have gases that are being generated, so such as the combustion of fuels, or if we are combusting foods to determine their energy content. And so what I'm going to show you next is a picture of a bomb calorimeter, which is where constant volume calorimetry often takes place. So if you look in there, you see that there is a pretty set amount of space in which the combustion process can occur. There is water surrounding that steel bomb area, and we can measure the temperature changes associated with that water to account for the reaction that's taking place in the bomb calorimeter. So what we're going to look at here is a neutralization reaction between hydrochloric acid and barium hydroxide. We see that that makes barium chloride and water, and that 118 kilojoules of heat is being released in this chemical reaction per 2 moles of hydrochloric acid consumed and per 1 mole of barium hydroxide consumed. We want to know how much heat would be released if you're going to mix 100 mils of 0.5 molar HCl with 300 mils of 0.5 molar barium hydroxide. We are told that both solutions started at 25 degrees, and we are given information about the final mixture. Its mass is 400 grams, and the specific heat is 4.18 joules per gram degrees Celsius. We want to know what the final temperature is of our mixture. So we need to figure out how we can use the information given in this question to get us there. If we want to know something about the temperature of the mixture, we're going to need to know something about the energy associated with that mixture. So we're going to need to figure out Q. And we can always relate the system to our surroundings. So we need to figure out, is the mixture referring to the system or is it referring to the surroundings? Water is a part of our reactants, but water is actually undergoing a chemical change in this reaction. It's the hydrochloric acid and the barium hydroxide. So the mixture is our surroundings. So we would be able to relate that to the energy released by the reaction. So that'd be our Q of our reaction. And remember that that amount of heat being released is based on the amounts of reactants and products we have. So although negative 118 kilojoules of heat is released by the hydrochloric acid and barium hydroxide, if we look, we see that we have a concentration and a volume given for both reactants. We need to determine how much of those reactants was actually used. So in order to find the Q of our reaction, we need to know how many moles of our reactant we had so we can set up that proportion and figure out how much heat was released for our reactants. So again, I know that might seem a little bit crazy. You always have to look at it from both the system and the surroundings perspective. What are we trying to find? And then how can we get there with the information we have? We have a Q value in terms of that delta H. That's specifically for our reaction, and because we want to find out about our surroundings, our mixture solution, we've got to use those to connect the two together. So we're going to work through this and actually go from the bottom arrow and work our way back up to the final temperature. So in order to find the moles of our reactants, we're going to multiply our molarities times our volumes once we convert our volumes into liters. And so if I take that reaction and I multiply 0.1 liters by 0.5 molar HCl, I get that I have 0.0500 moles of hydrochloric acid. I take the same volume and multiply it by its concentration, and I get 0.150 moles of barium hydroxide. Those are my two reactants, and I want to figure out how much product I can make from them. It really doesn't matter which product you choose to make with it. We just need to make sure we're comparing it to the same product so we know which one we're going to consume. I went ahead and just did water, and it doesn't again matter if I'm finding grams or moles, so I made this as simple as I could. Using the coefficients from the balanced equation, 2 moles of HCl for every 2 moles of water, and that gives me that 0.05 moles of water could be possibly made. If I do the same thing with barium hydroxide, this time it's a 2-to-1 ratio, and I see that I could make actually a lot more water, 0.3 moles. So what this tells me is that I will run out of hydrochloric acid before I run out of barium hydroxide, so hydrochloric acid is my limiting reactant. Why is that important? I said up at the top that negative 118 kilojoules of heat was generated by reacting 2 moles of hydrochloric acid. I only have 0.05 moles of hydrochloric acid that are being consumed. So now that I know how much hydrochloric acid is being consumed, I can figure out how much heat would be released in this reaction for the amounts of reactants I have. I have 0.05 moles of hydrochloric acid, and I know for every 2 moles of HCl, I will release 118 kilojoules of heat. So when I multiply those together, the 2 is an exact value, it does not affect your sig figs. I see that I actually only release 2.95 kilojoules of heat. That negative sign's there because it's exothermic, that much heat is being generated. And if you remember back to our first unit, we know that or the first lesson in this part of the unit, that if you have an exothermic change and you are releasing heat, then the temperature of your surroundings should increase. So we know what the Q of our reaction is now, either in kilojoules or joules, and with that information we can find the Q of the mixture, the Q of the surroundings. In theory, it should be exactly the same, just opposite in sign. If that's how much heat was released, the surroundings should have absorbed that much heat. Alright, and we also know that the Q of the mixture is going to be able to be determined by using MCP delta T. We have the specific heat of the mixture, we have the mass of the mixture, and we know the initial temperature of our mixture. So hopefully you're seeing now how we could get that final temperature. So the Q of the mixture, I went ahead and changed to joules since my specific heat was in joules. I substituted my mass, my specific heat, and my initial temperature. After going through and combining the constants together, canceling out the units that are the same, I get that 1.76 degrees Celsius is the temperature change that occurred. And so the final temperature would be 1.76 degrees higher than 25. And with sig figs, decimal places tell me it would round to 26.8 degrees Celsius. You can always take that value and substitute it back in and see if that gives you the approximate Q value that you've been asked to solve for. And when you get to this point, if you don't want to do the algebra, you can always substitute it into your graphing calculator and solve for the intersection. Alright, and you will not have problems that are this crazy on a regular basis, but you should be able to work through them if you are given one like this. We're going to do one with a bomb calorimeter now, and then I've got some practice for you to do with these. I think a couple of each. This time we have quinone, and we are burning it in the bomb calorimeter. It's undergoing combustion. We have 0.1964 grams of quinone, and we are told the temperature of the calorimeter, so that's that water that was in the calorimeter, increased by 3.2 degrees Celsius. We're also told the bomb calorimeter has a heat capacity of 1.56 kilojoules per Celsius. So we're going to figure out what the energy of combustion is for the quinone per gram and per mole. Your calorimeter has a constant volume, so the mass is independent. It still will affect the Q value for our reaction, but it does not affect the heat capacity of that bomb calorimeter since it's a constant environment. So that's why you don't see the mass in there, that you just have the net amount of heat that is being absorbed or released per degree Celsius. So the calorimeter in a bomb calorimeter situation, the energy associated with it is always equal to the heat capacity times the temperature change. And that energy, which is either being absorbed or released, is going to be equal to but opposite in sign of that of the reaction. So if we can calculate the energy change of the calorimeter, we can calculate the energy change of the reaction. We have the heat capacity, the 1.56 kilojoules per Celsius, and we have the temperature change, 3.2 degrees Celsius. They cancel out, multiply, and we get that the calorimeter absorbed 5 kilojoules of energy, which means the reaction released 5 kilojoules of energy. You are asked to find the energy of combustion, and that's what our Q of the quinone is, because it's the energy of the reaction that's taking place when we combust the quinone. But we want to find it per gram and per mole. So this is just the negative 5 kilojoules. We want to figure out what this would be for the 0.1964 grams. So to find it specifically per gram, we take that amount of energy and divide it by the mass of quinone that we burned. And that actually causes us to have a slightly larger amount, negative 25 kilojoules per gram, since the mass was less than 1. If we want to convert from grams to moles, we can either take that amount of quinone and convert it to moles using molar mass, or you can just go ahead and take the negative 25 kilojoules per gram and use molar mass to get you to kilojoules per mole. And this time it's going to be even a little bit larger, which kind of makes a little bit more sense. We've been seeing larger values for the energies associated with burning. So this should get you through the next worksheet, the enthalpy changes associated with chemical reactions. And as always, if you have any questions in class, please don't hesitate to ask.